I'm on my way to see Brent at Cerro Gordo, but I'm driving right through Death Valley, so I thought I'd do a quick video on the geology of Death Valley, some of the history, some of the gold mining, on my way to go see Brent. Our story is going to begin here. I am almost to the lowest point in Death Valley, but I want to show you these rocks here behind me. I'm going to hike up this wash. We're going to look at some of the oldest rocks in the whole basin. It's a long way running up that wash. These rocks here behind me are some of the oldest in the park. They're about 1.8 billion years old. They're about a third the age of the Earth, and it's deep, deep basement craton rock. And this is what geologists think make up the basement of the North American plate. And the reason why we're seeing them on the surface now is due to the very, very recent extension. These rocks are normally 10 or 15 kilometers deep, but because of the uplift and extension, we're able to see them here on the surface in Death Valley. So that's what it's like to touch almost 2 billion year old rocks. It's an interesting rock type. There's some, you can see they've been stretched and torn and twisted and abused. Stop number 2, we are at Mosaic Canyon. So we started with 1.7 billion year old rocks. We've folded them, metamorphosed them. That cratonic basement is what we call it, for about 1 billion years, a little bit more, 1.2 billion years. Those rocks have been on the craton, they've been eroding, and now, about 500 million years ago, we've sunken them in a shallow sea. And what happened, think of it kind of like the Caribbean. Nice, warm, shallow sea, and in that environment, you're starting to deposit limestone. Layers and layers and layers of limestone as the cratonic basement keeps subsiding. So as this slowly subsides, you're filling it up with limestone. And what you end up with is a stack of limestone sitting on top of this cratonic basement. So here's our first look at these limestone deposits. And these rocks actually are no longer limestone. They've been metamorphosed into marble. But we're going to use our imagination and pretend we're in a shallow sea, and each one of these little tiny layers is a deposition on the seafloor. And you can look at the types of rock even within the beds and see that things were changing over time. This stuff here has a little more sand in it. It's a little siltier. Maybe it was shallower up close to the beach, and then maybe here there was a down drop, and this is more limestone, less sediment in it. Then you have another little layer of sediment come back and more limestone. Could have been a storm that brought these sediments down, but you have layers and layers and layers, and as you look up the canyon, it goes for thousands of feet. There was thousands of feet of deposition. I'm walking up this narrow slot canyon. There's a lot of people on this trail, so I'm doing my best to film around them. But I wanted to show you on one side, this is the bedrock. This is the marble, currently marble, but when we've been talking 250 to 500 million years ago, this was limestone. And then on the other side of this canyon, you have a much more recent deposition of stuff washing down the canyon, coarse cobbles mixed with silt, and these have solidified into pretty much a rock at this point. And as you look up the canyon, the left side is the marble bedrock, the right side is probably considered bedrock as well at this point, but it's this conglomerate, this breccia that's washed down the canyon and has been deposited for so long that the limestone and the marble chemistry has worked on this to form essentially a concrete. These slot canyons are really cool as well. Currently, the current geology is that it's been uplifted in mountains and the water has run down these very narrow canyons and eroded a nice narrow canyon right down into the rock. When you have a fairly stable environment that's depositing limestone over about 250 million years, geologists call that a passive margin. It's very similar to the east coast of the USA. There's no subduction zone there. It's pretty much where the water, the ocean, meets the land and nothing much happens for a long, long time. And you just have this constant, even, slow deposition of limestone. So that passive margin is about to change. Something starts to happen about 250 million years ago. Our shallow, passive margin begins to change and begins to uplift. And when you have uplift, that's telling me that you have compression of the crust. And so our shallow sea begins to rise up onto the land. It becomes compressed and raises into hills and mountains. And during that process of the compression and the folding, and your limestone becomes heated and squeezed, and it metamorphoses into this marble and dolomite and things that we have now in the canyon. And from about 250 million years ago until about 65 million years ago, this process occurred, and it uplifted the whole southwest of the United States. So everything was brought out of this shallow sea, uplifted into these mountains, and erosion occurred. And once you start shedding all this sediment, the limestone, now marble, begins to erode. On the hillside back here behind me is a perfect example of layers upon layers upon layers of marble. And you can see as this whole region was being uplifted and those limestones that were deposited were metamorphosed into marble and dolomite. They underwent folding and faulting, and I hope you can see this, but right about here there's a nice big fold in the marble layers. I'm hoping you can see that from this far away. But this is an example of that uplift phase where you turned all that limestone into marble, the mountains formed, folding, faulting occurred, and then the volcanism followed shortly after. I'm driving through the far west side of the park now, and a lot of the rocks I'm driving through are basalt. And this is some evidence of volcanic activity in the region. The butte out in front of us there is a huge, thick, multiple flow flood basalt event. So behind me here as we leave the park to the west is a beautiful example of these flood basalts. And you can see the top layer of each episode oxidized and rusted, and then was covered by another layer successively in this huge layer cake of volcanic flood basalts. And since they've been deposited, a huge valley's been cut down by running water. And so as that crust started to spread and decompress, the lava made its way all the way to the surface and was able to flow out onto the surface in these huge flood basalt episodes. The next phase of activity from about 65 million years ago to about 3 million years ago is one of my favorites. That's when you have this volcanism, you have all this heat and this magma happening where the volcanoes were occurring, you had ash and lava coming out at the surface, and these granite magma chambers were hidden underneath the mountain. The very interesting part for me is the Sierra Nevada were building at the time. You had subduction occurring off the coast. The Juan de Fuca plate was subducting under California, but the boundary between the Juan de Fuca plate and the Pacific plate was starting to subduct as well. And it started at the very southern end of California, actually down in Baja. And as that plate margin started to subduct under the North American plate, the kinematics changed. And the contact between the Pacific plate and the North American plate became a strike slip fault, the San Andreas Fault as we know it today. When that occurred, volcanism started to shut off. and it slowly worked its way north along California, and the Sierra Nevada volcanoes started to shut off one by one by one. So when you're down in Joshua Tree in Southern California, those granitic plutons that you're seeing in batholiths, they are the oldest, the deepest, brought up from underneath to the surface because they were shut off first. As you move north into California, up the Sierra Nevada, the rocks are shallower and shallower until you get up to like Mount Shasta, where it's one of the last volcanoes where the Juan de Fuca plate is still subducting under the North American plate. Mount Shasta is about to get shut off. I am here on the west side of the park right now. I'm actually just outside the park to the west. I'm headed to Cerro Gordo, and I wanted to show you these granite rocks, these intrusive granite rocks here. These are the roots of mountains. And you can see the spheroidal weathering on some of the peaks behind me here in these little hills. What that's done in relation to the gold mining is all these gold veins were forming under the Sierra Nevada as that subduction was occurring, very similar to the Andes in Chile, where you have this plutonic magma, all this water circulating, depositing all these gold veins. Once that gets shut off and these mountains begin to erode, and you have those plutons and veins come to the surface, all the gold and all the gold veins start to erode out of these surrounding rocks and get deposited down in the valleys. And that's where the California mother lode comes from. But to totally blow your mind, you actually can have mountain building from erosion. So if you think of the North American plate as a boat, and you think of the mantle as the ocean, when you have all this volcanism occurring and you're building these mountains and bringing lava to the surface, your crust is getting thicker and thicker and thicker. As that crust gets thicker and thicker, it's like your boat that you're loading down with heavy rocks. So your hull sinks down into the mantle a little bit over time, and you filled up your boat, and your crust is very, very thick now. But if you take that crust and you shut the volcanism off and you start eroding away those mountains, you're unloading your boat. And so what does your boat do? Your boat floats higher and higher in the water. And so as you erode these mountains away and you shed all this sediment down and the gold nuggets fall down into the creek and all this stuff runs out to the west into the ocean, you're actually building a mountain range. You're exhuming all this stuff from way down deep by eroding the stuff off the surface. So that just blows my mind. And to tie some of this back into Cerro Gordo, where you have these very, very rich silver deposits, some of this volcanism that's occurring in these mountains could be occurring underneath the mountains in Cerro Gordo, bringing that hot fluid that we talked about and depositing those mineral deposits, all the galena and the silver, up into the limestone that's the mountains that Cerro Gordo's founded on. And it's the volcanism that's occurring deep down that's bringing all those fluids and all those minerals to the surface. And actually, as I went to get back into the car, I saw some tailings piles right over here on this hill. So mining activity right near these granitic rocks intruding into some of the surrounding limestone. You have these mineral deposits the miners are looking for. So there's a little bit of a large picture, arm wavy explanation of the volcanism occurring in the Sierra Nevada and farther east into Death Valley and beyond. But now let's head over to our last major stop in Badwater Basin, and we'll finish up our story there. Well, no video of mine would be complete without talking about gold mining. And I am here at the Keen Wonder Mine in the northeast section of Death Valley. And this was one of the few gold mines that actually produced some gold. It produced about $1 million of gold back in the early 1900s. I don't have a lot of time here. I'm trying to get to Cerro Gordo, so I'm sure this could be an entire day trip. But I wanted to give you a little bit of a taste of what I can see. And from what it looks like here, up near the mill site, there looks like there were some cyanide tanks down here. There's some old buildings, foundations, rusty metal. It looks like we have a tailings pile a little bit farther down in the valley here that you can see. And like any good mine, it had an aerial tram. You can see the supports there and the cable running up the hill down into what I'm assuming is an ore bin or a tipple. Like a lot of the gold mines we see and talk about, This one appears to have schist very close by. This is metamorphosed seafloor, and there's some outcrops of it here. Here's a little trail over to a small little adit there. A bunch of rusty metal. Looks like an old ore cart, or maybe a tramway bucket. And as I've talked about in a lot of the gold mines that I visit, the gold needs a couple different things. It needs a source for the precious metals, and the schist seems to be one of the most common host rocks for gold-bearing quartz veins. And so if you have the seafloor sediments that may have trace amounts of precious metals in them, the next thing you need is heat and fluids. And you can get those two things a couple different ways, but in the Death Valley environment, we had uplift and compression, which can create a lot of heat. You had volcanism and intruding hot magmas that can also bring in a lot of heat and a lot of fluids. And then the other thing that can do it is extension. When you spread everything out, you can get some heat coming up from underneath. And so when you have heat and fluid and a host or a presence of precious metals, those fluids can circulate through the system for millions of years, collecting and dissolving all those precious metals out of that schist potentially. And once it finds a fault, a crack, a change in pressure, a change in temperature, it can deposit all of those concentrated fluids into these cracks and veins, which form the ore deposits that the miners then go and mine. But what we have here is, it looks like the end of the tram, the tipple where the ore was stored, some sort of way to transport the ore down here, and I'm assuming it went down this valley, little valley right to the mill where we started. So that's just a little bit of the mining history of Death Valley. Like I said earlier, there wasn't a lot of gold deposits in the valley, not like the rich gold deposits to the west near the Sierra Nevadas or farther east inland towards Nevada. So Death Valley really didn't get very rich fluid deposition, but it does have some other mining history that's really cool. If you're here in the valley, check it out. There was some early mining that mined the evaporite deposits for borax and some other stuff here in the valley bottom. So let's move on to our next stop. And here we have a great shot of central Death Valley, looking up towards Stovepipe Wells on the right and panning our way across, looking south down the valley to our next and final stop, Badwater Basin. Here we have another pretty cool and unique feature of Death Valley. This is the Mesquite Flat sand dunes here behind me. And sand dunes are one of my most favorite active geological features. I really like them. I think they look really cool, and they're one of my least favorite to walk in. These are located kind of right dead center in Death Valley, kind of at the confluence of three main valleys. And this is the area where all the blowing quartz settles out, falls out. It's right behind a major mountain range, and so there may be an eddy in the valleys here where the sand ends up falling out. But when you look at the huge amount of sand out here, acres and acres and acres, some of these dunes are hundreds of feet high, and all of the sand has been collecting here for hundreds of years. Remember, this was a lake not too long ago, so this feature is very, very young. It's still very active, building to this day, and it's collecting all the quartz blowing around this valley. Here's an up-close look at the size of the sand. It's so uniform in size because only a certain size can be transported here. So if it's too big, it doesn't move and get transported. But if it's too small, it blows away. So this is beautifully segregated. It looks like somebody did it with a sieve almost. Today it's not very windy, so they're not very active. But when you come out here and it's windy, you can see sand blowing 5 feet deep. It's really pretty cool to watch. And these features are, like I say, they're still active, so they're changing, they're moving. The sand is getting deposited and moved all the time out here. But if you get a chance to visit, it's really, really neat to walk around the sand dunes a little bit. And as we move farther down into the valley floor, into the younger geologic record, at the very bottom of the valley here, where it's been extending and the crust has been thinning, we're running into rocks like these, volcanics. What this means is the crust has become so thin at the valley bottom, right where it's spreading, that magma has been able to come up to the surface and form these little cinder cones, like I'm standing on now. All the black across the way is all volcanics. And so this is more evidence of a super thin crust where the magma is actually able to find cracks to come up through and get deposited right down here on the valley floor on top of all the alluvium that's shedding off these mountains. And this is the last stop on our trip. About 3 million years ago, the subduction of the Juan de Fuca plate off the coast of California stopped. And what that did is it shut off all the volcanoes, and that vise, or that bulldozer that we were talking about, pushing against the continental plate. Once that went away, the entire continental plate started to relax and spread out and start to thin. And here at Badwater Basin, where I'm standing, is the lowest point in the United States at minus 282 feet below sea level. That is occurring because the entire continent is spreading out and normal faulting along these deep-seated faults, which force the plates apart, and these valleys form in the middle, dropping to very low depths. Even though I'm 282 feet below sea level here, there's another 11,000 feet of alluvium until you hit bedrock, which is the lowest point in this valley. And looking across the valley at the snow-covered peak, that's Telescope Peak, that's 11,000 feet above sea level. So what this normal faulting has done is spread this valley out, so you have over 22,000 feet of relief between the highest point and the very bottom of the bedrock valley. This has been occurring over the last 3 million years, and it is continuing to occur. The strike slip fault that is now off the coast of California no longer has that push, and so the continental plate is continuing to relax and spread out. In the more recent history, after the last ice age, it was a lot wetter and cooler here, and there was a lake that filled this valley. There are spots along where you can still see the old shoreline. It was up to 600 feet deep. But once the climate started to dry out and warm up, that lake has slowly disappeared and evaporated, leaving the salt flats that you see here today. The valley is a closed basin, so all the water that falls here stays in the valley, but because it's so dry, it evaporates away, leaving all of these salts and minerals left behind. So as the rain falls in the valleys and the mountains, it dissolves all these minerals, comes down onto the valley floor, and as it evaporates, it leaves these really cool salt deposits. Death Valley is oriented more or less north-south, and the extension is parallel with the coast of California, because that's where it's relaxing and spreading out once that subduction went away. So the whole plate is thinning, and as it thins, it's spreading out, uplifting blocks to the west and down dropping these deep valleys. And Death Valley is only one of the entire Great Basin area, basin and range area, where you have a series of deep valleys separated by large mountain ranges. And that's because the whole southwest United States is thinning and extending. Imagine a snow shovel for the last 65 million years pushing up against the continent. That bulldozer, snow shovel, putting it in a vise, whatever analogy you want to use, has stacked all these rocks up into a huge mound. And 3 million years ago when that shut off, the whole deck of cards is relaxing and spreading back out, and it's all normal faulting back into these big deep valleys and these mountain ranges that you see here all around us. And I'm standing in the very bottom of one right now. Because Death Valley is so dry, it creates these amazing alluvial fans. You can see them here behind me and on the other side of the valley as well. And over the last 3 million years, as this valley started to open up, the erosion has brought all the alluvium down the valleys, and it spreads out to these beautiful alluvial fans. If I remember right, they have about a 3-degree angle of repose. And out of every valley, all the way up Death Valley, is the spectacular alluvial fan, filling in the valley and bringing the mountains down into the hole that's been created by the extension. Behind me is where we started with the 1.7 billion year old rocks, and we end our journey about a quarter mile away at the very lowest point in the continental US. Well, now I'm off to Brent's to go see him at Cerro Gordo. We're going to do a lot of cool stuff there. So if you guys want to tag along in that video, be sure to subscribe. Thanks everybody for watching, and we'll see you on the next video.